So this is for folks who were gone last week. We went over this lab together. I wanted to just touch base with you guys on a few things. I think pretty much everybody was comfortable with 3, 4, and 5, and pretty much everybody was good with 6. Something that we did talk about last class was that when we're talking about net force, there's forces that are acting perpendicular to the ramp, and then there's the forces that are acting parallel to the ramp. So we're describing those as the forces in the x direction and the forces in the y direction. So when we're thinking about the x direction, that's going to be all of the stuff that is here parallel to the surface. So this would be positive x over here, this would be negative x back here. So it's just a coordinate plane that's been tilted. And so the forces acting in the x direction are going to be FGX, so the weight that's pulling me actually down the ramp. And then in the negative x direction, you've got your force of friction, which is why we would describe this as a negative number. Now, then you've got your forces acting in the y direction, and those are going to be these ones, anything that's acting vertically. Your normal force acting vertically in the positive y direction, and then you've got your FGY, and see how that is acting in the negative y direction. These are parallel here. So this is negative y down here. So these, we said that they are balanced in question number 5 because the marble's not accelerating vertically. You don't see the marble flying up into the air or crashing through the ramp, so these do have to be balanced. So that's how we know that these are the same. And technically, we would say FGY is equal to negative FN because they're going in opposite directions. So if this is a negative number, this is a positive number, is really what that means. You might feel more comfortable writing it like this: Fn is equal to negative FGY, but you can see that those mean the same thing. It's just showing that they're opposite direct size. Anyway, we know then that our net force acting vertically, net force in the y direction, remember the sigma, sum, means net, total, added together. That's 0. And then in the x direction, since we are assuming that there's no friction here, then there's only the one force. It's just this one. So then overall, our overall total net force, considering both of those directions, is FGX. So this is this right here, that weight that's pulling parallel to the ramp, that is the only unbalanced force that's acting on this marble. And so that is what makes the net force. All right, now, this is what I did in class last time, and so I'm just going to try to briefly go through and explain what we were talking about. So students worked on what would be the acceleration of the marble, knowing, of course, that if we have our net force, that net force is equal to mass times acceleration. Therefore, acceleration is net force divided by mass. So they're taking their answers, whatever they got to number 6, just divide that by your mass, and you should be good to go. Remember, the mass is going to be that really small value in kilograms. When we were weighing those marbles, it looked like it was 0.0282, so it will be a really small number. So whatever you get for your net force here, you're dividing that by it's a small number to start with, and then you're dividing it by a really small number, and so we get a number that's a little bit bigger, but still kind of small. Okay, so then these were like at 10 degrees, this is what people were getting. At 20 degrees, they were getting this, and at 16 degrees, they were getting this. So those are some values that looked accurate. Okay, and so then this was calculating using DAT-VV. We calculated what the final velocity would be. For this, I'm really looking for that you're using final velocity is equal to initial velocity squared 2 times acceleration times delta d, all under the square root, because remember that's v final squared is equal to that, so we have to square root everything. Okay, and then we have how much time should it take. So what I'm looking for is that you are using this formula. Acceleration is change in velocity over time, therefore time is equal to change in velocity over acceleration, not this one. This would be if you had a constant velocity, you would use this, but we don't have a constant velocity, so that's why we have to use this formula. Don't use this one. No, bad. Okay. Then if the marble is accelerating at a constant rate, I think pretty much all of you guys were good with the fact that the final velocity would be twice the average velocity. So then if we figured out what the final velocity would be here, the average velocity would just be half of whatever these numbers are, basically. So we're just trying to be able to compare apples to apples. Then we did some tests, and so we had one team, they had 1.93 as their value, their average time. Another team had 1.68, and then I just went through some practice calculations using the 1.93 just as an example, and so that's what's written here below. So I think I had a team, we did the distance of their ramp, so we're calculating an average velocity here, and so that's just going to be the distance over the average time. So we did the distance of the ramp was 1.836 meters. That number would be coming from whatever you measured your pipe length to be, or at least from like end to end. Some of you guys had kind of like a flattened part right here and here, and so it would be just that part that's going to be the straight piece is what we're looking for ideally. Okay, so then final velocity, back down here. Okay, so our average velocity is distance or divided by our total time, and that was the length of the ramp in meters divided by the average time in seconds, and we got this as our average velocity here. Then we're getting to, based on the average velocity calculated in 13, what should your final velocity be? Well, our final velocity should be twice the average velocity, twice as much, so we can figure this here. And then if we figure out what the actual acceleration of the marble is, what we should be able to do is figure out our change in velocity over time. So our change in velocity, delta V, that would be our final velocity minus our initial velocity. And so if our final velocity is 1.9 and we're starting the marble from rest, that would be 0. Our delta V is going to be 1.9 minus 0, which is where I'm getting this as my answer for 1.9 for my change in velocity here. Then I get, of course, the time, divide by that, and I should get 0.99 meters per second squared as my acceleration. Which, I think this was the 10-degree team, and that their acceleration they got up here was 1.7. Fairly off, kind of rough. We actually calculated a 73% error on that one, which is rough, definitely rough. And so we talked then about why would this be the case. Any of these labs where you're having to time by hand, it's just hard because it's that reaction time. So, you know, there could have been some other issues here. We're not totally sure. Some of the other teams actually got a really, really great percent error, which is awesome. But what we also wanted to talk about here is what are we actually comparing? Because in this situation, comparing the acceleration to our predicted acceleration, we're not actually comparing apples to apples right now. Remember, this acceleration, we calculated that with the assumption that there is no friction. So this error is not just about a timing error. This is also about the fact that the predicted value did not take any friction into account. Granted, the amount of friction that we ought to actually have should be pretty low with an object that's rolling, and it's, you know, it's not a perfectly smooth marble, but it's relatively smooth, and pipe is not too rough either. We should be getting a value somewhat closer to what we've got here. So we should be getting a pretty good amount of coefficient of friction. This difference is pretty huge. Then let's see. So what we got to here, actually, yeah, because that was 0.74, which was a crazy high amount of friction. This is like rubber against a carpet. This is definitely not a marble on a ramp. This was one of the ones that another team got, who had that just seemed a much more reasonable value. Some coefficients of rolling friction are right around in here, 0.0 something, usually like between 0.01 and 0.05. And for the surfaces that we were looking at, we looked at some tables online and found that about 0.041 to 0.049, those were some good ranges. So you'll see on the next activity that we're using 0.045 as our coefficient of friction. So that's what we were hoping to get here. What we're dealing with in number 17 then, what is the actual net force on your marble based on the your actual acceleration calculation? Well, then we would say mass times the actual acceleration, which was the 0.99 that we got part 14. And so then that is what the net force would be using that. Our net force, if we then want to figure out how much our force of friction is, what we're actually doing is adding the two objects that are, or the two forces that are acting along in that x direction. So we're now considering that force of friction does come into account here. And we're saying that we have, saying that we have a tiny amount of friction. This answer comes from, we're saying our net force minus our force in the x direction, gravity in the x direction, force due to friction. So what we're saying here is that our net force in the x direction is those two added together. We've just subtracted FGX over here. So we did our net force 0.028 minus what our force due to gravity in the x direction was, and so we end up with a force due to friction of negative 0.020. That is what then allows us to do this formula. Net force of friction divided by normal force gives us mu, and since that is scalar, that's why we put these lines here to show that that's an absolute value, because if we just divided those two, we would be getting a negative number, but we know mu doesn't have a direction, so that's why we did that. And then we found 0.74, which is crazy high. So not totally sure where of error for that are. It could be a few different things. But in any case, that is what we did on this page. Thanks.